Finally! So EDTA is a common chelator that we use, and that means that it bites down around metals and it can hide them from things like proteases and nucleases. So things that'll chew up proteins and nucleic acids that maybe we weren't wanting to study. So it's really, really helpful, and so we make these highly concentrated stock solutions that we can then add small amounts of these to whatever we're working with in order to make it. To have EDTA in that reaction. But making the stock solutions is a big pain because in order to get EDTA to dissolve, you're going to have to add a lot of NaOH. So NaOH is a base and EDTA is an acid, and what happens is that the EDTA, when it's in its acid form, water doesn't want to hang out with it, and metals doesn't want to hang out with it, so it's insoluble and it's not effective as a chelator. But then as the pH raises, the EDTA starts deprotonating, and so these positively charged protons get pulled off, exposing negatively charged groups, and the lone pairs on the nitrogen that can coordinate with metal. And so therefore, as you add the base, you're able to dissolve the EDTA. But you have to add a lot of the base in order to get to do this, even if you start from the salt. So do yourself a favor and start from the sodium salt rather than just like the base. This is going to be easier. It's kind of like partway deprotonated already, and then you take it all the way with the NaOH. But when you're taking it with the NaOH, but then it's dissolving, then you have the EDTA dissolving and deprotonating. When you're deprotonating, the protons are getting released, so now you're lowering the pH again, and so the pH keeps going up and down and up and down, and you don't want to overshoot. So it's a long process, but here's basics of how it works and how to prepare a stock solution of EDTA and its related partner EGTA, which is more selective for calcium over magnesium.
Okay, so we'll start with the practical stock making stuff, but if you stick around till the end, you can hear a bit of a rant about how EGTA is almost always drawn wrong, and it drove me crazy. But anyway, let's start with how we make an EDTA stock solution. So again, the most important thing is that we need to remember that we're going to need to add some base, and we're going to add NaOH, so sodium hydroxide, because we already have sodium, typically because we're starting with a disodium salt dihydrate. So again, this is the version of EDTA that already has two salt ions with it, but it still has these protonated nitrogens and is therefore inaccessible for binding to the complexing with the metal. And so we need to add NaOH to strip off those protons and get it into the state that can dissolve and act as a chelator. And so how much so we need to add? So our basic overline is we're going to weigh out what we need, calculate what we need, weigh out what we need, add it to dissolve it in a little bit of liquid, leaving enough room to add the NaOH to adjust the pH and get things to dissolve. And then finally adjusting the pH to where we want it, adjusting the volume to where we want it, and then sterilizing it. So we need to start by calculating how much we need to add, and this is going to depend on what we want our final volume to be and what we want our final concentration to be. Typically, we're dealing with molarity. So when we're talking about molarity, we're talking about like copies of things per liter. So a mole is 6 times 10 to the 23rd of something. We call that like Avogadro's number. It helps us work with really tiny numbers in a more convenient form. It's kind of like a dozen, except that we're talking about way, way, way more than a dozen, but the molecules are way, way, way smaller than bagels typically. And so it works out well. So that's mole. Molarity is going to be moles per liter. And so when we talk about a 1 molar solution, that would be 1 mole per liter. Often when we're making with an EDTA stock solution, a convenient concentration is going to be 0.5 molar. So it's the same as saying 500 millimolar. You can make different concentrations if you want. Typically it would be a lower concentration. Your you want to have a high concentration, but you still want it to be able to dissolve. And so all these molecules have a solubility limit. So when you're choosing what concentration to do for a stock solution, typically the best thing to do is just like to Google it and see what people normally make. And you can also check the solubility limit, and then you want to make something that's practical and easy to work with. And so you could make a 0.473 molar or whatever, but that would be a pain to calculate with. But again, often you want to use like what people normally use because that's probably best. And then if recipes call for it, you have it. So anyway, I like to make a 0.5 molar solution at a pH of 8. So how do I do this? So we need to figure out the molecular weight or the formula weight for EDTA. And again, because we're dealing with this EDTA disodium salt dihydrate, so we have those two sodium ions and 2 water molecules per EDTA molecule. That means that when we're calculating this, like when we're when we're weighing things out, we need to take that into account. So when we're talking about molarity, what we really care about is the number of moles of EDTA. But when we're looking at the formula weight on the bottle, what we're seeing is in terms of that whole complex. So we have EDTA, we have 2 sodiums, and we have the 2 waters. Those sodiums and waters are going to weigh things, and so when we have that added weight, it's going to contribute to the formula weight or the molecular weight. So it says molecular weight here. Often people just say molecular weight, but in this case, it's actually a formula weight because molecule technically is everything has to be covalently bound, and these aren't covalently bound. We're not going to get into that. And just know that the molecular weight on this MW, that's going to stand for your molecular weight or your formula weight. And in this case, if we look at the disodium salt dihydrate, or disodium dihydrate, we see it's 372.24 grams per mole. For some reason, sometimes they don't write it on the bottle, and then we have to write it on the bottle ourselves. And this is going to be higher than the formula weight for the anhydrous or waterless EDTA. So this is the version without salt and without water. You can see that it has a lower molecular weight. So this is telling you that a mole's worth of it is going to weigh less because you don't have all of that other stuff to take into account. Remember, this formula weight is going to take into account the whole Kim and the caboodle, or whatever the phrase is. And so you have to take into account the things that come along with it. Whereas in this form, it's just alone. So when we're calculating, if you're starting from this salt, you want to use this number. And if you're starting from the anhydrous, you want to use this number. But again, it's better to start from this disodium salt. It's going to make your life a lot easier. But if you don't have it, then you want to use what you do have, and then you need to use the appropriate formula weight. Okay, then you have to figure out how much you want to make. If you look up recipes, they'll often make like a liter, but that's probably just like because of ease of calculations. That's a lot of EDTA, and I don't think you typically would go through that much EDTA, at least very quickly, unless you just make it because like a whole liter at a time because it's a pain to make. But still, I don't think I went through like more than, I don't know. I don't think that's a lot of EDTA. But maybe you do use that depending on your applications, I guess. Okay, so anyway, I decided to make 500 mils. So I calculated what I need. And so basically just dimensional analysis. I have a post on this if you're confused about it. But I end up making it so the units cancel out and end up getting that I need to weigh out 93.06 grams of EDTA. Now my balance only doesn't go that exact. So round to what your balance does do. So 93.1. It's quite a bit of EDTA. Okay. And yeah, it's again, so make sure that you know what you're using. There's also tetrasodium EDTA, tetrahydrate. And at first you might be like, okay, well, why don't I just use that? So that would be the version of EDTA that is already like totally deprotonated. So you think like, oh, that'd be nice. Then I don't have to add any NaOH, right? Problem is, if you were to dissolve this in water, it would dissolve, but it's going to give you a pH of like 10-ish. And that's going to, if you add that to your reaction, it's going to like kill your proteins and stuff. So you don't want to do that. And so we want to only take things like part way, basically. So we start with that disodium salt, and then we deprotonate it a little further, but not like all the way, or at least not all the copies all the way. And how we're going to do this is going to be adding NaOH. So we weighed out what we need, and now we need to add it to the water. So we're going to, remember, we're going to be needing to add, we're going to have to take into account both the volume of all that EDTA powder, as well as the volume of any NaOH we add. So we want to make sure that we leave plenty of room when we add it to the water. So just a note, when you're adding it to the water is, I would like to put the water in first in the stir bar, and then add the solid to it, so that you don't want to put the solid in there first and then pour water on top, or you're just going to get a big clump, and then you try to stick your stir bar in and the stir bar won't even move. Or if you have like the stir bar and the solid in there and then you add water, then the stir bar just gets like stuck in this yeah, don't do that. So you want to put in about like 2/3, 3/4 of the volume of water total, and then with the stir bar, and then you can add in the solid. And remember, it's not going to dissolve yet. So when you do that, you can see that if you have your pH probe in there, you're going to see that the pH is going to start going down, down, down. So you can see it's around like 4.6. So you need to add that NaOH in order to get it to dissolve. It's going to take a lot of the NaOH. And so what I like to do is start with NaOH pellets, so this like solid sodium hydroxide. You can start with a concentrated solution, but then you're going to have having to add a lot of that concentrated solution, which is going to take up volume, and it's going to waste your concentrated solution, which you had to take time to actually make. Basically, when you make a concentrated solution of the NaOH, you were dissolving it in water. And so now basically why we can skip that having to make more of it later for other purposes by just going and using the pellet straight from the pellet. But you want to, the bad thing about the pellets is it's easier to overshoot things, but that's why we start with it, and then later we can fine tune and go dropwise with the concentrated solution. I think it took me about like 9 grams or so of the pellet. And you can see that when you add it, it's going to raise the pH. The pH is going to start going up, 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 up. And you can keep adding. So you get up there and maybe you overshoot it and you freak out. Don't worry about that, because it's probably going to come back down. And so what happens, just don't try to overshoot it, but what happens is that as the EDTA dissociates, so as it like dissolves and those protons get pulled off, well, now when you're adding free protons, remember that's like pH is a measure of proton availability. The more protons there are, the lower the pH. So as you're releasing those protons, you're lowering the pH. And so you have to go through this constant battle between adding NaOH and watching the pH go down. And so finally, you want to make sure that it's all dissolved too. So when you definitely don't want to overshoot it after everything is dissolved. So when things are still dissolving, if you overshoot it a little bit, I mean, not talking like majorly overshoot, but if you overshoot a little bit, then you can be like, okay, I know it's going to come back down a little, so it's okay. And you can squirt in a little more without having to worry, like squirt a little less carefully in terms of how much you put in. You can squirt larger volumes, knowing that it could still go down. But once it's all dissolved, well, now you're out of luck if you want to go down. So you want to be really careful at the end when you're adjusting the pH. And then finally, you get to where you want, and voila, it's now time to filter things. Just a note that if you don't need the pH to be exact, then it's okay if it's not like perfect. But make sure whatever you do, make sure you put the pH on the bottle. If you do need it to be exact, then you're going to need to be careful, because if you overshoot, you can't just add acid to bring it back down, at least if you want to make it the proper way. So you might be used to making a buffer or something where you add NaOH to make it, to raise the pH, and then add HCl if you go over to lower the pH, so you can fine tune the pH. We're going to do this a lot when we're making a buffer because it's easy to go over and under and things like that. Well, we can't just add HCl in order to bring the pH down, because we don't have chloride ions in our solution right now. And so we don't want to add them in there. Typically, when we're adding like an acid or a base, we want to add something that's already in there. So we're only changing the concentrations of what's already in there, and only like changing the pH that way. If we do add HCl, then we're also introducing the possibility of making like table salt, and we are changing the ionic strength, so how salty the solution is and things like that. So you don't want to add HCl to bring things down if you overshoot, if you want your solution to be pure. But if that's like, if you want it to be pure, just like practically speaking, if you have to add a couple drops, that's probably okay. But if you want it to be really perfect, then you would need to start over. Okay, you're almost done, but now you need to adjust the volume. And so you want to adjust the volume to that final volume that you had. And this is why, remember, it was really important that you left enough space, because now at this point, you're pouring it into the graduated cylinder and crossing your fingers you didn't go over. So the lines on the beakers are only approximate. And so you want to make sure that you're not going above the line of the beaker when you're stirring, or like when it's in the stir. But remember, the stir bar adds a little. So if it's a little over, it might be okay. But anyway, you want to pour it in. So make sure you don't pour the stir bar in. So I like to hold a magnet on the bottom and then pour the solution in. And see, I left plenty of room. And then I could fill it up to the top with my pure water. And so for all this, I'm using milliQ water. Okay, so now final step is to somehow sterilize it, typically. And so I filter sterilized it. So I have this vacuum top, or this bottle top filter. Another option is to autoclave it. So I actually use this nitrocellulose membrane, which is, it binds to proteins. And so hopefully this is going to get rid of RNases if there is RNA contamination, because an autoclave won't get rid of that. But yes, and then the 0.2 micron, so it'll filter out like bacteria and weird mold and stuff like that you don't want grown in there, because our whole purpose is to keep things like clean and away from all those nasty stuff. Okay, you can use something similar with EGTA. So because I don't use EGTA as often, I only made 100 milliliters of it. And this stuff is more powdery. It's kind of like powdered sugar looking. But anyway, for 100 mils of a 0.5 solution, weighed out 19 grams, took about 4 grams of NaOH, and I made it in just the same way. Some of the recipes for EGTA say to store it in the fridge. Some don't. I store mine in the fridge just because better safe than sorry. Okay, now finally, as I promised, the rant. So basically, this might remind you of a rant that I've had in the past when it comes to how amino acids are drawn. So amino acids actually hang out, so these protein letters, they hang out in this zwitterionic form, which I love an excuse to say zwitterion. So I'm going to get to say it today as well, because EDTA can hang out as a zwitterion. So a zwitterion is where you have a positively charged part of a molecule and a negatively charged part of the molecule, and it's neutral overall. This is not the same as polarity. So this is polarity, but it's like not all polar molecules are zwitterionic. With zwitterionic, you actually have like full charges. With polarity, you can have partial charges. So with this zwitterionic molecule, you have positive and a negative, and then molecule is neutral overall. Amino acids hang out this way, but you often see them drawn in this state that like does not exist, this like non-ionic form. So you can see, like, if you were to say, like, draw a neutral form of an amino acid. So if you, this is the correct way, but you see it drawn like this all the time. So why is this wrong? Why is this wrong? Is because the nitrogen wants the proton a lot more than the oxygen wants the proton. In its carboxylic acid form, this oxygen is really happy because this resonance stabilized, all's good. It's not, if it takes a proton, if it protonates, it's going to lose that resonance and it's not going to be as happy. So it's not going to take protons unless it's at a really, there's a ton of protons available, which means there's a really low pH. Whereas the nitrogen, it's happier to take a proton, and so it's going to protonate more easily than the oxygen. And so if you're at a pH that's low enough to protonate the nitrogen, you're going to have protonated the oxygen. And if you go down in pH, you're going to protonate that nitrogen before you protonate the oxygen. And the exact same type of thing is happening in the case of the EDTA. So when we go down to a really low pH, yeah, we'll get those carboxylic acid groups protonated. But before we get those protonated, we'll have protonated these nitrogens. And so the neutral form of EDTA is not this version where you have all the carboxylic acid groups as carboxylic acid as opposed to carboxylate. So carboxylic acid is where it has the H, carboxylate is when it's deprotonated. So it's not like this. Instead, it's like more like this, where you have two of those deprotonated so that they cancel out the two protonated nitrogens. And so as you go down in the pH, you're going to protonate so if you start from this like fully deprotonated state, when you go down in the pH, those nitrogens are going to protonate, and then the oxygens are going to protonate. And so you'll see it drawn like this all the time, but it can be really confusing when you actually try to think about the biochemistry that's going on. So just be aware of that. And when you have the chance to draw it, don't draw it like that, because yeah, that is not, no.